So far, it's really pretty much been the tracking like we saw before. But now, the particle filter tracking, where you've got a model and you're tracking it. But the thing that we're going to do now that's a little bit different, this is sort of the cool part, is we're not going to assume that our appearance and observation model remain constant. Basically, the idea is we're going to sort of update the model as we get new images coming in. Now, a sort of a standard way of doing this, and by the way, this works really poorly, so don't do it, is I have a model appearance, I look around, I say, ah, that's my best one, and I say, okay, I guess it's changed a little bit, let me pull out that model, and I'll find that in the next image. And eventually what happens is you get drift, and the model lands on that. There's this really, really cool thing over, oh, you can't see. Okay, I'm going to pretend like there's this really great car sitting right over here, and eventually and just get stuck on there, and the thing that I was tracking would go away. But if I don't update my model, then as things change, I can't find it so well anymore. So what we do here instead is, with every new appearance, we're going to change our eigenbasis, right? This is the set of eigenvectors that lets us reconstruct. We're going to change that a little bit. And that allows for a small variation in appearance, but it's still going to try to do things like track the general class. And so the trick is, just as it's written here, given the basis set B of t minus 1 that we use to find the observation at time t minus 1, that allows us to compute a new eigenbasis, B of t, that we're going to use now to evaluate our measurements. All right? So the idea is that we're updating this eigenbasis, but it's adding it's a small variation each time, so we can't radically change what things look like. We can change them a little bit. And this is referred to as an incremental subspace update. As you remember from PCA, we said the whole reason that we're doing this dimensionality reduction is the idea that we believe our images lie in some subspace, but we have to find that subspace within the bigger feature space. So that's why this is referred to as an incremental subspace update. And why are we doing this? Basically, we're accounting for appearance change. So we might be tracking the object in the image, it's translating, it's rotating, it's maybe sharing. But if I rotate out of the plane, as far as the camera is concerned, my face is changing its appearance. As I go sideways, it usually gets worse, but that's okay. The idea is I want to model that change. So we're learning a new appearance representation as the imagery changes. In the papers that I've been telling you about, they base it on this recursive SVD algorithm, which is kind of nice, so you don't have to do the whole eigen decomposition again, so you can do this quickly in real time. That part doesn't matter so much. Essentially, what you have is an algorithm that allows you, it's kind of like a running mean algorithm where you're using the most recent examples more strongly than the older examples.